Problem 33. Here we have two objects. You have this disk and also that ring. Both of them are connected to the wall at point O here, and we are releasing them from rest, from this position. And the question is, what is the reaction force at O in any of these, and also what is their angular velocity. Angular velocity is equal to 0 because we have just released them. What is the angular acceleration at the beginning, immediately after releasing them? So again, to solve any of these problems, both of them are going to have same method. We need to draw the free body diagram of them. In this one, we have two reaction forces, OX and OY, and also we have gravitational force, mg. Same thing goes here too. We have mg here, and also two reaction forces, OX and OY. Because we are just releasing them, we are talking about immediately after release, velocity of both of them is equal to 0 at this moment. So there is no angular velocity. But it doesn't mean they don't have angular acceleration. It is possible to have angular acceleration in both of them. You can assume it is clockwise or counterclockwise. It doesn't really matter. But we know it's going to be clockwise, right? Because they're going to start to rotate in this direction. For both of them, we have these two equations. Sum of the forces in any direction is equal to the mass times acceleration in that direction. And sum of the moments about the centroid of them is going to be I times alpha, right? So, and what coordinate you are going to use is up to you. You can use normal tangential, or we can simply use just xy coordinates. I'm going to use xy coordinate for both of them. But we need to talk about the acceleration of the centroid of these two. So look at point C in both of them. Point C is moving on a circle about point O, right? So acceleration of it is going to have two components, if you remember from chapter 5. Whenever you have a point which is moving on a circle, it's going to have normal acceleration and tangential acceleration. The normal acceleration, an, is equal to velocity squared divided by r, but the velocity of c at the moment is equal to 0. So there is no acceleration in the normal direction. The only acceleration they're going to have is going to be r times alpha. So acceleration is going to be r times alpha, which is the tangential part of the acceleration. Again, there is no normal acceleration at the moment because there is no velocity. Same thing goes here too. Acceleration of c is going to be just r times alpha, and it's going to be downward because we assumed alpha is clockwise. Knowing this, now we can write the equation. Sum of the forces in the x direction is equal to mass times acceleration of the centroid, which is c, in the x direction. But there is no acceleration in the x direction. So OX, which is the only force we have in the x direction, must be equal to 0. Same thing goes here too. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. So OX is going to be equal to 0. Sum of the forces in the y direction is equal to mass times acceleration in the y direction. In the y direction, we have OY minus mg is going to be equal to acceleration in the y direction is going to be negative r times alpha because acceleration is downward. So I'm going to have negative m times r times alpha. Same thing here. Sum of the forces in the y direction is equal to mass times acceleration of the centroid in the y direction. So OY minus mg is going to be equal to negative mr times alpha. Negative, again, because the acceleration is in the negative direction in the y direction. So the last equation is sum of the moments about the centroid is going to be ig times alpha. And what moments do we have? Moment of mg and og, they are 0. Both of them are passing through a C. The moment of oy is going to be oy times r in clockwise direction. So it's going to be equal to I times alpha in the clockwise. Both of them are in clockwise direction. So I'm going to have oy times r is equal to I about the centroid, which is C here. You can write G or C. It's up to you. Times alpha. But what is I for a loop, for a ring? If you remember, we said mass moment of inertia of a ring, about the centroid of it, about the axis of it, is going to be mass times r squared. So Oy times r is going to be mass times radius squared times alpha. Or you can simplify one of these r's, and Oy is going to be equal to mr times alpha. We have this equation and also this equation, which relates Oy and alpha together. If you solve them, we are going to have Oy is equal to mg divided by 2. And alpha is going to be g divided by 2r. We can do the same thing for the other one. The only difference is I of a disk is different than I of a ring. Sum of the moments about g is equal to ig times alpha. Moment in clockwise direction is going to be Oy times r. This force and this force, they're not going to make any moment about point C. Is equal to ig for a disk, if you remember, is equal to half of mass times r squared. This is the mass moment of inertia of a disk about the axis of it, times alpha. Again, we have this equation and this equation for O and alpha. If you solve these two equations together, Oy is going to be equal to 1/3 of mg, and angular acceleration is going to be 2g, 2/3 of g divided by r.